Hello viewers, I Dr. Mala Das Sharma welcome you to my video number 131 of my channel MALACHEMPHILIC. And video number 131 is the 70th episode of Chemical Thermodynamics where the topic is concept of fugacity and fugacity coefficient. So let's start. Fugacity and fugacity coefficient. Lewis introduced the concept of fugacity for representing the actual behavior of real gases, which is distinctly different from the behavior of ideal gases. So, fugacity was introduced to represent the behavior of real gases. Fugacity replaces pressure in the real gas. So, in real gas, in place of pressure, we write fugacity. So, it is the effective pressure of the real gas. Now, coming to the physical significance of fugacity. To understand the physical significance of fugacity, you just consider that in a beaker, water is taken, okay, and above this water vapor is there. That means water is getting vaporized and converted to vapor which remains above this liquid water, and it is closed. Okay. And now again what will happen? This water vapor gets condensed and comes back to the liquid state. So from the liquid state, water molecule gets vaporized to the vapor state. And again, this from the vapor state, water molecule gets condensed and coming back to the liquid state. Right? When this rate of evaporation becomes equal to rate of condensation, then it is in the equilibrium. So at equilibrium, rate of evaporation is equal to rate of condensation. Now, fugacity means this escaping tendency from the existing state to the other state. So, each substance has escaping tendency from its existing state to the other state. That is the physical significance of fugacity. That is represented by fugacity. So, fugacity is the escaping tendency. So, each substance in the given state has a tendency to escape from that state. This escaping tendency was termed by Lewis as fugacity. Okay. Now, see, we know that dG is equal to VdP minus SdT for reversible process. Now, differentiating, if we differentiate, so differentiating with respect to pressure at constant temperature. Then what we'll get? We'll get dou G by dou P at constant temperature. That will be is equal to V. So, what we can write? dG is equal to VdP. Now we know that for ideal gas, your PV is equal to RT for 1 mole. So, V is equal to RT by P. Now, in place of V, I'll write RT by P. So, dG will be is equal to RT, then dP by P. Right? So, this equation, I can write this form. dG is equal to RT d ln P. Okay. This is one equation. Right. Now, integrating. If we integrate this equation, integrating this equation, that means your dG will be is equal to, means integration of dG is equal to RT integration of d ln P. What will be this integration result? It will be G. G is equal to RT ln P plus this integration constant, say G star. So how can I define G star? See, when P is equal to 1, that means this term will become 0. Then G is equal to G star. So integration constant G star is the free energy when the pressure is equal to 1. Right? So we got that dg is equal to RT d ln P, that equation, and this is our another equation. These are all for ideal gas because there I put V is equal to RT by P from this ideal gas equation. So once again I'll write dg is equal to RT d ln P. Now integrating between the limits. Integrating between the limits. Then what it will be? Say G1 to G2 dg, integration of dg, RT outside of the integration sign, then P1 to P2, then d ln P, right? Then what it will be? That is G2 minus G1, that will be is equal to RT ln, or G2 minus G1 means I can write it is as delta G. Okay. So here itself I'll write this is delta G is equal to RT, integration of d ln P will be ln P. So ln P2 minus ln P1, that means ln P2 by P1. So ln P2 by P1. So this is another equation. And these all are for ideal gas. Okay. So for ideal gas, what all equation we got? We got that is, one is your dg is equal to RT d ln P. Another one we got G is equal to, this is your G is equal to RT ln P plus G star, this equation, RT ln P plus G star. And then another one, delta G is equal to RT ln P2 by P1. All these equation are for ideal gas, and these are all for 1 mole of ideal gas. If you multiply by N, nRT dln P, nRT ln P plus G star, nRT ln P2 by P1, then it will be for N moles. So these all are for ideal gas. Okay. Now for real gas we can write. So we can write for real gas, just we have to replace the P by F, fugacity. What we can write? dg is equal to RT d ln F. Then you can write G is equal to RT ln F plus integration constant G star. Then we can write delta G is equal to RT ln F2 by F1. All these are for real gases. Already I have written above. Okay. Only difference is in place of pressure P, we are writing fugacity F for real gas. Right. Now, Fugacity of a real gas related to its vapor pressure by the following equation. F by P, this ratio is denoted by gamma, and gamma is the fugacity coefficient, which is the measure of deviation of real gas from ideal behavior. Okay. And we know that at very low pressure, that is pressure tends to zero, intermolecular attraction between the gas molecules decreases. Okay. So almost all the gases behave ideally at very low pressure. So when pressure P tends to 0, then this gamma actually fugacity coefficient is 1. That means limit F by P is equal to 1. That means F is equal to P, fugacity is equal to pressure, because gases behave ideally at very low pressure. So gamma fugacity coefficient is equal to 1 at very, very low pressure. That means the gas behaves ideally. Now unit of fugacity is same as that of pressure because it replaces pressure in real gas, and gamma is a ratio, so it does not have any unit. Understood? So what we got? We got F by P, that is equal to fugacity coefficient gamma. So from here what you can write? F is equal to gamma into P. Right? Now already we have seen when gamma is equal to 1, then your F is equal to P. That means fugacity is equal to pressure when fugacity coefficient is 1. That means the gas behaves ideally. So this is for ideal behavior. Okay. Achha. Now, when second case, when this gamma greater than 1, this gamma is greater than 1, then what will happen? Then F will be greater than P. F will be greater, that is fugacity is greater. Fugacity more means escaping tendency is more. That means here repulsive forces dominating. Repulsive forces dominating means escaping tendency more. Escaping, or we write more escaping tendency. More escaping tendency. Right? And then when gamma is less than 1, gamma less than 1 means then F less than pressure. In that case, these attractive forces between the molecules dominating. So, attractive forces dominating, what does it mean? That is less escaping tendency. Fugacity less means escaping tendency is less. Okay. Coming to the determination of fugacity. Determination of fugacity. Graphical method. Graphical method. We know that dg is equal to vdp. Right? Again we have seen dg is equal to RT d ln f. Now we introduce another term alpha. Alpha is V ideal minus V real. Volume for ideal gas minus V real, for real behavior. So what we can say, alpha is the deviation from ideal. Alpha indicates the deviation from ideal behavior. Okay. Right. Now, for ideal gas, for ideal gas, what do we know that PV is equal to RT for 1 mole. So, V is equal to RT by P, right? So, what we can write, alpha is equal to, as we have seen that, alpha is equal to V ideal minus V real. Okay. Now, in place of V ideal, what we can write? We can write alpha is equal to RT by P minus V. That means V real for real gas. So, therefore, we can write V is equal to RT by P minus alpha, right? Now we have seen that dG is equal to VdP, and again dG is equal to RT d ln F. Okay, so we can equate these two. Therefore, what we can write? We can write RT d ln F is equal to V dP. Here this V is for the real gas, right? So in place of V, what we can write? RT d ln F is equal to V means RT by P minus alpha into dP, right? Into dP. Okay. So here we can write it as RT d ln F is equal to RT dP by P minus alpha dP. We can write it, then divide it by RT. Then what we will get? We will get d ln F, that is equal to, this will be, this RT get cancelled. dP by P, I can write it as d ln P minus alpha dP divided by RT. I can write integrating the equation between the pressure P from 0 to P. Okay. Then what we will get if we integrate this one? So it will become ln F, that will be is equal to ln P 0 to P, no? So only upper limit, and then this will be minus 1 by RT, then integration 0 to P alpha dP. This is the equation. Or once again I can write ln F by P is equal to your minus 1 by RT and then 0 to P alpha dP. Okay. Now, if we want to, from this equation, look at here, this pressure is known. If you want to calculate this fugacity F, then you should know the value of this right side integral, right? So what was our equation? ln F is equal to ln P minus 1 by RT integration 0 to P alpha dP. This is the equation. Now, so as I told you, if you want to calculate this fugacity, this P is known, you have to know the integral, this right side integral value. How to calculate that one? The value of alpha plotted against the corresponding pressure. The area under the curve between the pressure 0 to P is the value of this integral. That means what you have to do when we are plotting this alpha versus pressure, okay, this is alpha, this direction, and this direction your pressure, and this is here alpha is equal to 0, and here your alpha is positive upper side and down alpha negative. Okay, if you plot it, you will get this type of plot. Now, this area, here alpha is positive, this area is giving this value, that means this integral 0 to P alpha dP, and this is positive. And here 0 to P alpha dP, and this is, here it is negative. Okay, so this area will give the value of this integral. Is the deviation from ideal behavior. Okay, so alpha may be positive or negative. From the graph, what do you observe? That alpha is positive at low pressure. So we find alpha is positive at low pressure. Okay, so when alpha is positive, therefore the fugacity will be less than pressure, because pressure minus these things. Okay, therefore at low pressure fugacity is less than ideal pressure. Okay, now then alpha is negative at high pressure. We are observing negative at high pressure. Okay, so if it is negative, positive, that means the fugacity, that means therefore at high pressure, fugacity F greater than pressure. Okay, so fugacity will be less than pressure at low pressure. When the pressure is high, fugacity will be greater than the pressure. Okay, and this fugacity can be evaluated at any given pressure of the gas. So what we have found, that fugacity is to represent the behavior of the real gases, and it is the escaping tendency from the existing state to other state. And fugacity coefficient indicates the deviation from this ideal behavior. Hope you have understood. Thank you.